Uh, Today I'm gonna talk about a tool called project minimization, especially for it aims for a minimization of Kotlin compiler errors. Okay, let's start from the yeah, let's start from the problem overview. And yeah, basically Kotlin has some errors, and so on. And sometimes users come with some wrappers of these errors. They attach their projects with a lot of code and a lot of different things, settings, and so on, and also attach probably the errors they have met. But since the projects are quite big and so on, QAs looks at these projects and look like this. And they try to reduce the project to make a smaller example with the same error to better understand the error, better debug them, and then fix. And yeah, it's quite complicated task, and probably sometimes it's unsuccessful. Requires a lot of time and effort because there are different settings. The QAs should delve into the project that users sent and so on. And after some minimization, for example, we can receive something like this. It's much more simpler and understandable, and devs can easily debug this and fix the error. And since the problem is to minimize, to get this example from the bigger one, we aim make a tool that automatically minimizes the projects to retrieve something like smaller examples of the same error based on the provided projects. So yeah, and let's start with the overview of the state-of-the-art approaches that exist. Yeah, there are basically two main approaches called delta debugging and program slicing. And the difference between them that delta debugging is highly adaptable for any domain and can be easily extended by anything, but it's completely slow, dramatically slow. So yeah, that's the main problem of this. And there is a program slicing, which is advanced technique. It's extremely fast, but it requires more effort to implement it. For example, we should implement some different analysis like data flow analysis, control flow graphs builds, and so on. And let's delve into these two approaches. Let's start from the delta debugging. And for example, we have such code, and it's quite simple. The first step that we should do is split this code into some smaller items. It can be anything. For example, it could be something like lines, or even something smaller and complexer like functions, or even something hierarchical like trees, like AS10. And then when we've done this with splitting into items, the aim of the delta debugging is to try to find some smaller subset as smaller as possible, that will reproduce the same issue, the same error. And this is a general NP-complete task, and so we cannot just iterate over all subsets and try every subset with compilation and so on. And there is an algorithm approximation that is based on something like a binary search. How it looks like? The first step, we divide all items into groups with the same size, and then we try to remain every group without others and test with these items and delete the others one. For example, take the first 4 items, the second 4 items just delete, and then try to execute compilation on the provided project, and then we receive some result. For example, we can receive that it's successfully completed, and it means that we just throw out some important thing. And it could be different here. For example, on result reference, we just throw out the class that is required for the retained one, and also we can receive something that we need, basically the target here. And after this, we receive some smaller groups, or probably we just cannot throw anything. Then we divide the rest groups again into 2 groups, each group divided into 2 groups with the same size and so on. And we repeat the procedure, like trying to delete only one group, retaining all other groups. Or then if we successful in this, so we received a smaller example, so we continue to reduce the number of groups and so on. And at the end, so when we receive that each group consists of only one element, only one item, we're trying to throw out only one item. And if we reached that we cannot throw anything, we have finished. So, and as a result, we receive something smaller, probably not. And of course, this algorithm is not the best one, because approximately the number of compilations that is required for the algorithm can be something n⁻², but yeah, it's much more faster than NP complete task. So that's the algorithm, the simplest version of it. And what's the problem of this algorithm? Why it can be not succeed goodly? For example, in the middle of the procedure, we can produce some code like this. It can be syntaxically wrong. It can be just, for example, with different error, like we throw out the needed function, for example, for the error. But anyway, there are a lot of such problems. And that is why this algorithm is not so good and extremely slow. Of course, there are some modifications that try to solve such problems. For example, there are modifications that just speeding up the approach, or even that works on trees, or even that modification that works respecting the context-free grammar of the language. But of course, for example, from such problems, it's not a solution, but that's the best that we have now. And yeah, let's look at how we implement some algorithms on the practice, and we'll look at the real problems on real projects that we have. For example, the first algorithm that we have implemented is a file level minimization. It's basically hierarchical delta debugging modification, and it looks like we have this structure of the project. We choose the first level. It can be models, for example, and execute the usual delta debugging to try to delete something. For example, we can succeed in deleting some model, and as a result, we delete a lot of files, a lot of code, and will reduce the number of REST calls dramatically. And then, after we succeed with the one level, we go go deeper, like to the next level, and try to do something like again just delta debugging. And as a result, we receive something like this. And why it's better than trying to just throw in files at the beginning. For example, if we just trying to execute the also debugging, usual debugging on the last level, immediately we will receive a lot of compilations. We will receive probably worse results, and instead of it, we're just at the beginning throwing out all unused models, all models that are not related for the target problem, and receive the better results. The next algorithm is function level minimization. It's more interesting because it's not about reducing the size of the code. It's mostly about reducing the dependencies between items. Like, for example, we have such code, and after the function level minimization, we receive something like this. And how it works? We just get all bodies of the functions and trying to just replace the bodies, like deleting them replacing with some neutral statements, like to-do statements for Kotlin. And as a result, we in practice we receive something like only one function with body and other functions like with to-do statements. And the best results from this is that we have a lot of unused functions, a lot of unused classes, and code looks like a lot of something unconnected classes, files, and so on. And it can be easily minimized without any problems that we can delete one file with one class that uses in another. These problems are solved by this minimization partially, but yeah, that's a good one approximation that we can make here. And moreover, delta debugging on such cases works well because there is only one problem with replacing with to-do statements is that we just throw in the important one. Other problems are like we don't have other problems with this because we cannot delete some declarations, we cannot delete some symbols, we just deleting the bodies of the function, and for completion, it's not so important. So yeah, and the last delta debugging algorithm that we have implemented is declaration level minimization, and it applies hierarchical detail debugging on the program structure interface, basically, but it's like abstract syntax tree of the program. And for example, we built the abstract syntax tree for the class, and it's look like this. And then we execute on just the same algorithm as a file minimization. And it's extremely slow, because on such minimization, we have dependencies between symbols, like one function returning another class, which is used another class, which is used another class, and so on. And yeah, we cannot minimize it well. It works extremely slow, and basically the 90% of the test of the received code ends with the result reference error. And yeah, that's the main reason why the declaration level minimization is so slow. And moreover, it's not minimized so well as expected, and so on. Other problems with the other algorithm are basically the same. Like file level minimization works well only when we have a lot of code that's unconnected with each other, like unconnected models that are work separately. So for functional optimization, the only one problem that is just useless in vacuum without other algorithms, it's just reducing the dependencies between symbols. So yeah. And since the problem we have here is we're just not considering a lot of information, like usages of the function, where one class uses another class in some way. We can try to just let's make an algorithm that considers all these dependencies, and we here near the program slicing algorithm. And if I will simplify, it works like this. We just can build the graph with all dependencies that are present in the program. Then we identify the needed nodes that the target nodes where we have a problem. For example, from where we have an exception, compiler tells us about it, and so on. And then we try to traverse this graph, retrieving a smaller example with only dependents and dependencies of the target nodes. For example, it can look like this. We have such graph, and 8th node is the target node, and we just traverse in and get all dependencies and retains only dependent nodes. And it works well on the first look. For example, we can identify that error function uses add function, so we cannot just delete add function without deleting error function, and so on. But there are problems. We cannot consider all dependencies between all classes and so on in case of compilation error. In case of dynamic analysis or something like this, we can expect that we have almost all information about the program, but in the compilation, it's not true. And moreover, it's quite complicated to identify that which nodes are really needed to reproduce the bug. For example, this is a real bug from one of the latest versions of Kotlin. For example, we have some model with some interface object and extension function, and another model with function that calls extension function on the, well, you see this. So, and also we have an interface that is basically unused. But the main problem that's here, that if we will delete the interface B, we won't reproduce the initial error. And so the compilation error is placed here, but we cannot receive this information that we need for this error, also interface B. We have an information that we need this stuff because we can just traverse over all dependencies, but we cannot reach the interface B and the same model with the test function. So the program slicing will just delete it, and as a result, we will receive incorrect code for for minimization, because it's just has the difference here. So it means that program slicing is applicable here, and after it, we can try to make something that considering all these dependencies that we know, but also considering that we don't know any some dependencies between some objects, and we don't know where the actual error is, and we need something combination of these approaches, like delta debugging and program slicing, and the basic idea is let's try to modify delta debugging because it's easier than modifying the program slicing, basically, and try to consider known dependencies that we can retrieve from analysis, some static analysis. So basically there are two ideas how to respect this information. The first one is let's try to apply the usual delta debugging on the program, but before the testing, the actual compilation, we will also check the graph that's with dependencies and try to understand if there are unresolved reference before the actual compilation. This works well. It's faster, but it basically changes nothing. It's just a pre-check of the tests without actual improvement in the accuracy. So yeah, it will be faster, but with bad results. So there is a second way that's forcing the algorithm trying to choose the good, only good subsets of items to check whether the program has the same issue or not, but what are the good and how to choose the good sets. And let's look at the previous example. Here, what is the good set of the items? It means that we retain the all retained items have all necessary dependencies. Basically, it means that in terms of directed graphs, that we have a cut. Generally, it means that we have some retained items and deleted items, and there are no edges from the retained ones to the deleted. And yeah, that's the definition just of the good choosing of the sets of items. And so we just want to try to iterate over cuts, somehow choose cuts which will produce the normal code without any problems with unresolved reference and so on, or basically reducing these problems. And then we just iterate it over and over, like in Delta debugging, splitting into groups. We will split using some we will split the items into 2 groups using cuts. Also, there are some requirements for that. We need the make test as few as possible, because each test is a compilation, and compilation is quite long operation and so on. And yeah, the basic property also that we should reproduce the initial error. So yeah, the difference between the usual Delta debugging is just that we chosen only cuts. That's it. And the first algorithm that we have implemented is called GraphDD. And the first step to implement it, we just need to we have an observation that if one class dependent on another and it depends on the first one, we cannot delete them separately. We need to delete them only simultaneously or retained only simultaneously. Generally, it means that we can extract the strong connectivity between strong connectivity components, and then we can treat with these components as a single item, because we cannot delete any single item in the component without deleting another one in the same component. So yeah, we're reducing the graph into something like this, and there is no cycles here. It's important because it can break some. It's easily work with directed uncyclic graph than with graph with cycles. So basically, yeah, that's the reason. And then we trying to make something similar with how we made with trees. We need to split the graph into some layers. For example, we can split such graph into the layers where each layer doesn't contain any edges, but yeah. And after it, we can just execute the Delta debugging on such layers, but from the sinks to the sources. Why? Because if we will try to delete the first sources, the items without any dependent other items, we will receive we will iterate over the layers extremely slow, because we just will delete one item by one, and that's it, and it's extremely inefficient. So basically, we will change the order of the layers from the sinks to the sources, and we'll try to delete as much items as possible. For example, if we will try to delete the chosen one on the slides, we also will try to delete these ones. And yeah, that's it. That's the simplest version of the algorithm. It's basically the same as the algorithm with the trees, but we just respecting the dependencies that has the program. And yeah, here we have not a tree, but we can build some sort of tree on this and use this same algorithm. And the result that we retrieve from these modifications from this modification is that we have a project, for example, with 5,000 lines of code, and the usual declaration level minimization works about 2 hours, and as a result, we receive almost not so good results, like a lot of lines of code still there and so on. But when we apply the GraphDD, it works only 6 minutes, and as a result, we receive just a minimal result as we can possible to receive here, and that's it. So this algorithm is just changing the order of item that we traverse over, but it brings us a lot of results here. And of course, there are some optimizations of the such algorithm that we have not implemented because we have no time, for example, and we have no examples where we need really to improve only algorithm rather than other things, for example, considering other items. But anyway, here's an idea how to make better approach, combined approach that will bring more results. For example, we can define some metric on the cuts, and then perform some sort of search on the cuts, trying to maximize the number of successful deleted items per one test, leading to minimizing the number of tests. So yeah, basically the idea described here, for example, we choose some metric, find the cuts that maximize this metric, test on this cut, then adjust the metric according to the results of the test, and so on. And what metric can we choose here? For example, we can choose something that, as I said, trying to represent the maximum gain that we will receive from testing the cut. So basically, it means that we want to compute expected value of gain. And to compute it, we need to define something like probabilities, some model that computes the probabilities of the successful, to compute the probability of the successfulness of the test. For example, we can use here a Bayesian network on the dependencies because, dependencies. And probabilities will mean that something like likely in the answer should be in the answer, and so on. Then we should try to find the cut that maximizes the expected value of gain, which is just the number of deleted items when the test on this cut is successful. So then when we found a cut that maximizes this expected value, we just test on this cut. And if the test is not successful, we can try to update probabilities respecting the results of the test. For example, it means that we shouldn't delete some items that we deleted for the test. So that's just basic posterior probabilities computation, but that needs to be done. And then we just iterating over and over while we are not sure that there is no item that can be deleted. And there are some problems here. For example, inference of the Bayesian network is basically NP hard, as well as finding code that maximizes this metric. So, and of course, there are some solutions that try to solve such problems. For example, we can use some approximations, for example, using Monte Carlo methods or something. And for the search of the cuts that maximizes the gain, the expected value of gain, we can try to use, instead of normal search, some sort of local search techniques like genetic algorithms or something different. Yeah, and basically, I think that it will improve the results a lot, but we cannot test it right now. So it can be a good, I don't know, bachelor test maybe. Well, yeah, and that's it. You can try for example, our tool from downloading from the GitHub repo or something, and probably try to implement something different or anything you want. If you're really interested in something like making a new algorithm for, I don't know, for something, or just interested in this STEM, you can just write me somewhere. And yeah, that's it.
Thank you.